Hey, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on field extension. So remember last time we went through the definition of a field. So let's let F be a field. What does that mean? It's a set of numbers, usually, mathematical objects, and it needs to satisfy three conditions. So firstly, its elements need to form an abelian group under addition. Secondly, its non-zero elements need to form an abelian group under multiplication. And thirdly, it needs to respect the distributive law. So in other words, multiplication needs to be distributive over addition. So they were the conditions for a field. So what's a field extension? Well, it's where you take a field F and you adjoin to it one or more elements that aren't already in the field. So in this case, I'm just going to adjoin one element and call it alpha. So we want sort of alpha to not be an element of the field, otherwise we'd end up with the exact same field. It wouldn't be a field extension as such. So F of alpha is a field extension. So what actually is it? What it is the set of all numbers of the form A plus B times alpha, the thing that we've adjoined, and A and B need to be elements of the original field. So it turns out that this set here will also be a field. So to see that, let's look at an example of an actual field extension. Let's take Q. So remember, that's the set of all rational numbers that can be written as a fraction where the denominator and numerator are integers, and we're going to adjoin to it the square root of 2. So the square root of 2 is not a rational number. You can't write it as a fraction when numerator and denominator are both integers. So what will this look like? So this will be the set of all numbers of the form A plus B times root 2, where A and B are elements of the original field, in this case, the set of rational numbers. So let's go ahead and look at why this would still be a field. So let's first look at it being a group under addition. We want it to be an abelian group, okay? So let's first look at closure. Will this be closed under addition? Well, if you add two numbers of this form together, you'll get another number of that form. So let's look at that more closely. So if we add together a number like this and a number like this, so remember, we will be able to change the order of this addition. Why is that? Because these are real numbers. A plus B root 2 will be a real number. We know the real numbers are commutative under addition, so we can write it like this. And then thanks to the distributive law, we can factor B plus D. So it's a rational number plus a rational number times by the square root of 2, because two rational numbers added together gives another rational number. They're closed already because Q is a field. So this shows that they are closed. So secondly, we're going to look at the additive identity. Well, that's clearly still there. The additive identity 0 is in this field extension. It's just 0 plus 0 root 2. That's an element of this. All of the rational numbers are still there, including 0. So then, thirdly, we need to look at inverses. Well, that's pretty easy too. If I have a number like A plus B root 2, its additive inverse is just the negative of that. And that is of this form. That will be a rational number plus a rational number times root 2. So for example, if you have 3 plus root 2, then its inverse will be minus 3 minus root 2. If you add these two together, you get 0. And both of them are of the correct form. So lastly, we're going to look at whether or not this is associative. And we don't actually need to prove anything here because, as I said before, these numbers are real numbers because that's a field itself. they're always associative under addition, so I don't really need to check anything. So we could go through and show that the same is true under multiplication. So I won't do that because it's sort of the same idea, but what I want to do is just quickly go through multiplicative inverses. So you might be saying to yourself, well, hang on a minute, the inverse of root 2 is 1 on root 2. So this doesn't look like it would be of this form, something plus something times root 2. But it actually is, and the reason is, you know how you have fractions like, 3 over 4? You can times top and bottom by 2, and you don't change the value of the fraction. 3/4 and 6/8 are the exact same thing. So we can do a similar trick here. We can times top and bottom by square root of 2. This is called rationalizing the denominator. So if we do that, we actually get 1 times root 2 over root 2 times root 2, which is 2. Square root of 2 times square root of 2 is 2. And you can write this as a half times root 2. So suddenly this is looking of this form. So a half root 2 is just 0 plus a half root 2. So the inverse of the square root of 2 is actually inside the field extension. So that shows that an element of this form has a multiplicative inverse which is in the field. So the last thing that we needed to show in order to show this was a field is distributive law, okay? But again, just like associativity, that follows from the fact that this is a subset of the real numbers. All numbers in this field extension are real numbers, and so they will follow the distributive law. They will distribute multiplication over addition. Okay, so I didn't go through all the axioms of a group under multiplication, so please convince yourself that this satisfies all those axioms and ask me if you need any help. But that's what a field extension is. It's where you take a field and you adjoin to it one or more elements not in the field and you set it up like this. So I just need to quickly go through the degree of a field extension and algebraic and transcendental numbers. So what is the degree of a field extension? Well, it's just the degree, remember that's the highest power of the minimal polynomial. So the minimal polynomial is a polynomial that satisfies three things. So firstly, its coefficients need to be in the original field. Secondly, the adjoining elements need to be roots of that polynomial. And thirdly, it needs to be the polynomial of the lowest degree such this is true. That means it needs to be irreducible. So what the hell does this all mean? Well, that is a tricky definition. Let's look at an example and hopefully this will become clearer. So let's look at our example of q with root 2 adjoined. So the minimal polynomial, we want the polynomial with rational coefficients. We want root 2 to be a root of this polynomial. And we want it to be the polynomial of lowest degree that satisfy this. So the minimal polynomial of q root 2 is actually just going to be x squared minus 2. So let's call that fx. Okay. So, why is this the minimal polynomial? Well, firstly, it's monic because the leading coefficient, the number in front of the highest power of x is 1. So, it's monic. So, it needs to have coefficients in the original field. It does because 1 and negative 2 are both rational numbers. Root 2 is a root of this because if I substitute x for root 2, I get square root of 2 squared minus 2, which is 0. That's what a root is, a number that you can substitute for the variable to make the polynomial equal to 0. So it is a root. Now this is the polynomial of lowest degree that satisfies this because this polynomial cannot be reduced any further. So that means the degree of the field extension q root 2 is equal to 2 because the highest power in the minimal polynomial was 2. The degree of the polynomial is 2, therefore the degree of the field extension is 2. So let's look at another field extension. This time we're going to take Q and we're going to adjoin to it two elements, root 2 and root 3. So note neither of those, root 2 or root 3, is rational. So we know that the minimal polynomial of root 2 is x squared minus 2. We just showed that. So by a similar logic, the minimal polynomial of root 3 will be x squared minus 3. So the minimal polynomial of this one, this time I'll call it gx, so we can just times these together, x squared minus 2 times x squared minus 3. So this will have a root of square root of 2, this one has a root of square root of 3. So note if you substitute square root of 2 or square root of 3 into this whole polynomial, you get 0. Both of these are roots of this polynomial. So if we expand it using FOIL, we've got x squared times x squared, and so on. You get x to the power of 4 minus 5x squared plus 6. So this is the minimal polynomial for which root 2 is a root and square root of 3 is a root. Why is it the minimal polynomial? Well, note, again, it's monic. The number in front of the highest power of x is 1. All the coefficients 1, minus 5, and 6, they are rational numbers. And this polynomial turns out to be irreducible. It is the one with the smallest such degree. You cannot find a polynomial of lower degree that will have this and this as a root. So the degree of this field extension, again, it is the degree of the polynomial, the minimal polynomial, and the degree of the minimal polynomial here was 4, highest power was 4, so the degree of the field extension is 4. Unfortunately, sometimes you will adjoin an element to a field that is not the root of a polynomial with coefficients in that field. So that's what transcendental numbers are. So we now quickly look at transcendental versus algebraic numbers. So as I was just saying, an algebraic number is one that can be written as the root of a polynomial with coefficients in the field. A transcendental number cannot be the root of a polynomial with coefficients in the field. So it's important to note the field that we're talking about. So what I mean by that is let's consider the number pi, which we know is irrational. So that is transcendental over the field Q, because I cannot write a polynomial with coefficients in Q, coefficients that are rational numbers, where pi is the root of that polynomial. That is impossible. Any polynomial with coefficients in Q cannot have pi as a root. But of course, pi would be algebraic over the real numbers, okay? So I could easily write pi as the root of a polynomial with real coefficients. So it would just be the root of the polynomial, for example, x minus pi. Okay, if I substitute pi into this polynomial, I get 0. Of course, this has a coefficient here of minus pi, which is not a rational number. So this is a polynomial with coefficients in the field R, but it's not a polynomial with coefficients in the field Q. So it's important that we make that distinction. So just to let you know, when most mathematicians are talking about algebraic or transcendental numbers, they're really talking about algebraic or transcendental over Q. They usually just don't mention that. It's normally implied that we're talking about polynomials with coefficients in Q, but I just want you to make sure that you understand that you really should specify the field over which the number is algebraic or transcendental. All right, I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.